All right, let's get started. Hello, welcome everybody who's joined us today. My name is Andrew Willig. I'll be moderating today's webinar entitled MAPS, HEBI's new NDT technology. Please note today's webinar will be recorded and the recording will be made available shortly after the conclusion of the webinar. As we go through the presentation, all attendees will be muted, but feel free to send us questions through the chat feature located on the GoToWebinar menu bar. We will go through those questions live for our presenter throughout the presentation and demos. I'd like to introduce our presenter today, Dave Rollinson. Dave is co-founder and mechanical/controls engineer here at HEBI Robotics. Dave, take it away.
Thanks, Willig. Yeah, I'm Dave. Thank you guys for joining. We're going to talk about MAPS, HEBI's new product for non-destructive testing and inspection, the Modular Absolute Positioning System. Before I get going on talking about the system, what it's capable of, I want to give you guys some background on HEBI as a company, our technology, where it came from, and kind of the path we took to get here today. So we'll start off with a video there. So HEBI started off at Carnegie Mellon in the biorobotics lab, where we worked on snake robots, modular snake robots, called the ModSnake project. And this was a really great crucible for technology. It drove a lot of interesting development in both hardware and software, and it had a really challenging application. The goal was to get sensors, particularly cameras, into places that you can't get technology to normally. Looking at things like inspecting pipelines, inspecting nuclear power plants, urban search and rescue. And so the founders of the company were all researchers in this lab. And as we started moving beyond our research and looking for ways to commercialize technology, we were looking for how can we bring snake robots to the world. And what basically we established was the real nugget, the real useful piece was the underlying technology, those Lego-like building blocks that we built those snakes out of. So HEBI was started in 2015 to bring that technology out into the world in a more general purpose form. We want to create smart Lego-like building blocks so that robotics experts and non-experts alike can start to really experiment in the field, have this being underlying technology that we can use to really bring robotics outside of the factory from in the places where it's traditionally dominated. So in 2016, we released this X series actuator, this red actuator that you see here. And as we sold it to customers, all researchers, we were also looking for applications ourselves. So internally, we're also using these same tools, focused more on industrial automation, trying to figure out tasks, ways that we can leverage customizability. If you can build a robot that can do anything, what sort of mechanical design things can you do? But really mostly in terms of behaviors, right? So we want to make arms that are compliant. We want to make them lightweight. We want to make them safe. We really want to be able to have people bring really human-like manipulation to machines and try to get robots out of the factory, out of kind of a typical thing where if you want to make a million of something and do the same thing over and over, we're trying to look beyond that, right? We want tools where you can customize, where you have a lot more flexibility, a lot more variability. So at the same time, our customers around the world, right? So we're selling these actuators as well to others, and they're doing some really amazing things in them. One of our favorites to talk about is NASA Ames, which made this robot they call the Super Ball bot. It's a tensegrity robot, so the actuators control the tension and change the lengths of all these tubes so that you have a robot that can compact into a small shape and also move over really challenging obstacles. This is a potential design for a robot that they might send to the outer moons of Saturn, where they really have no clue what the terrain would look like. We have researchers in Korea at the Korea Hydronuclear Power Organization, and they're creating next generation robots to explore the insides of nuclear power plants. And so again, these are robotics experts where they're taking our actuators, they're literally providing the rest of the robot itself. We are the experts that provide actuation and that motion control layer of a robot. And finally, we have a customer who basically created a bolt-on self-driving car kit. So bring your own actuator, bring your own camera, computer, and I guess bring your own pickup truck, and you can get up and, this guy was up and running in a few months with our technology as well. So really a wide range of use cases. We're really driven by what we're seeing, the variety of what people are capable of when they have the right building blocks. But really the limitation up to then had been basically being able to take it outdoors, right? These are more targeted toward indoor environments. So in 2019, we released the R series actuator, which basically let us take these same set of tools, these building block tools, and move them outside of an indoor environment, and finally tackle some more challenging applications where really kind of the limiting factor is just the ruggedness of the hardware. So we basically built on these previous 3 years of work, and working with some partners in the oil and gas industry, particularly Chevron, started creating robotic arms to automate and assist the inspection of non-destructive testing, particularly measuring the thickness of things like pipes, tanks, vessels, all things that require kind of a compliant human touch, all things that are highly variable, but also all things where you want to really measure what's going on with as much detail as possible. So at the end of 2019, we were able to take the system out to a refinery and really try it in the field. The focus here was on pipe elbows and being able to take just a simple UT thickness sensor and getting as much information as possible, get full coverage of a pipe elbow in an automated way. And these trials were quite successful. The customer was very excited. With really just maybe 1 or 2 years of work, this arm, I think it will be in a state where it is really ready to change what you can inspect in an automated way. But in the interim, while we're working on that, what we found was a lot of excitement really just around the data. So as this arm's moving, it's measuring where it's going, it's collecting this data. And what you see here is we're able to do things like build up a 3D map, right? So you can truly see the thicknesses and the information about the pipe kind of in the context in that 3D view. And the real focus was that was the important part, maybe even more so than the automating. So what HEBI has done now this year is released MAPS, which is basically that system that you saw there, that automated system, but it's completely passive. So it's lighter weight. It consists of these 2 degree of freedom knuckles. So degree of freedom is a joint, in our case, something that rotates. So you have put these knuckles together, and what you have is a modular, flexible system that measures exactly where a probe is in space. And what we're going to demonstrate here are a couple different ways of using this tool, some of which will interface with existing equipment today, and some of which we think really moves the world of industrial inspection forward, particularly for things like corrosion mapping and taking a probe and getting full coverage of a pipe. But at its core is basically an arm that you will bolt to a surface. It measures the position of a probe in kind of full 3D, and then uses software to figure out that position on a surface. So with that, I'll go back to the presentation. Okay. So MAPS, the Modular Absolute Positioning System, excuse me. Yeah, just discussed. We're going to present, let me show my webcam here, I'm sorry. We're going to present a kind of two flavors, 2 versions of it that we see as kind of major use cases out of the gate. The first is as an absolute encoder that's compatible with any flaw detector that has encoder inputs. So there are systems out there that inspect pipes, particularly for ultrasonic thickness, and they take encoder inputs so that you can use wheels with encoders to move across the surface. So you would take a wheel and move it across the surface, and the system is kind of a drop-in replacement for that. We'll also demonstrate an integrated kind of end-to-end solution for doing UT thickness, particularly for corrosion mapping, that does not use an external flaw detector. And there are some next generation capabilities that, because we're marrying that thickness data with the full 3D information of the arm, we think that really moves things forward and hopefully breathes new life into kind of a very established inspection technique. So the first I'm going to go into detail about is that absolute encoder case. So it has the advantages that this arm basically plugs into your existing flaw detectors. So if you have things like an OmniScan or an Edify Gecko or a Zetec Topaz, again, really anything that has encoder inputs, we can work with that. There's no wheel encoders to slip, so the whole arm operates by basically clamping a base somewhere in space, and then once you've clamped that and kind of registered your surface, you know where your probe is at all times, kind of within a bounded amount of accuracy, as opposed to with wheel encoders, whereas if they slip, you kind of technically now have no idea where your probe is. So you're reliant on the operator and the equipment to be very, very consistent in the field, and you really have no observability after the fact as to whether or not the probe was really where you thought it was. The system covers a wide range of surfaces. So rather than having separate scanners for different geometries of welds or different types of surfaces or round tanks or flat plates, you have one piece of equipment that can cover a much broader range, or maybe even just, and because it's customizable and reconfigurable, a smaller set of equipment can cover a wider range. And then lastly, when you're using an existing flaw detector, we're really not changing or disrupting anybody's process at all, right? They're using the same workflow for the data. The reports look the same. The scans look the same as if it had come from a traditional scanner. It's just that you're now able to apply it to multiple surfaces. So the modes that we'll demonstrate shortly here are kind of two applications. The first is weld inspection. And so again, this would be something that you plug into any range of existing flaw detectors. And the steps are, the first thing you do is you take the arm, and once you fix the base, you take the end of your probe, like literally the probe that you're going to inspect with, and you touch different points, around the weld that you want to inspect. Once you've done that, our software connects it with smooth curves, and what we are then able to do is basically stretch that curve out into a straight line and have that become your B-scan. So you can set up your phased array probe the way you normally would with like a wheel encoder system, but now you can follow kind of that complex curve, and no matter what it does, you're figuring out where you are kind of in one dimension. So again, this plugs into anything that would normally have wheel encoder input. It's just that you can now follow you can follow a much more complex surface, and again, it's absolute. So even if you pick up the probe and put it back, if you need to go back and overwrite data, you can do that. If you need to do subsequent scans at different offsets, basically once you have that line set up, you can reliably figure out your location along that line. The second application we'll show is also corrosion mapping. So the weld inspection is sort of a one-dimensional case. In a two-dimensional case, you can lay out a grid of points. And again, this can be loosely done by hand, because what the software does is then connect these points with a set of smooth curves. And similarly to just how we can unwrap a single line, we can now unwrap an entire map, kind of as if you're, just like putting a map on the surface of the earth, right? You can stretch that out and wrap it. And where we think this really fits in is particularly filling, in addition to just covering more complex surfaces, it fills in gaps around things like taps, nipples, nozzles, places where you wouldn't be able to get an automated scanning solution today because some part of that workspace is obstructed. With maps, you can fill in those gaps and kind of get hopefully the best of both worlds between data as if it came from an automated AUT system, but still have the flexibility of a human operator to fill in all these nooks and crannies. The second part that I'm going to demonstrate is an integrated UT thickness solution. So on the left is kind of what we like to compare it to as a baseline, which is a UT grid inspection. So if somebody needs to get more than just kind of a single point of an asset, they will basically grid out a set of points, maybe at a 1-inch density or 2-inch density. And once they've painstakingly labeled out all these points, they go and they take a probe and they'll hit each one of them. And what we will allow you to do is basically virtually put a grid on the surface, again, kind of no matter what it looks like. And to start off with, in the case of pipe elbows, we'll show that we have some things that really speed up that process. Again, just like with if we're interfacing to an external flaw detector, there's no wheel encoders. Things are still absolute. the interface that we provide in this, because we are marrying the thickness in real time to that 3D data, you're providing intuitive operator feedback, where somebody knows kind of how far along they are in the process of inspecting. They can more intuitively see areas that they've covered, areas that they haven't, because they can pick up the probe and move it. Right? There's no need to carefully maintain contact with the surface at all times. So if there's part of the inspection that an inspector has to basically put the probe down, walk around, pick it up on the other side, they can do that because we're just keeping an absolute reference at the same time. And lastly, again, we cover a wide range of surfaces. The arm I'm going to show here has 9 joints, but the system can go down to 7, could be extended up to 11. Link lengths can be changed. There's a lot of work that we can do to make sure that the system is as versatile as possible. So instead of putting out that grid of points, what you'll get instead is a 3D, basically thickness map, a C-scan of the data. And aside from that being more intuitive, a key thing that you get when you marry the thickness data with the 3D information is it allows you to automatically align and compare scans over time. So rather than having, if you come back, if you come back and you need to do a scan, whether it's a week later or 5 years later, comparing that isn't, right now, at worst, you're just taking 2 numbers in a spreadsheet and seeing how they change, really not knowing what went in behind those numbers. At best, you might have scans that are flat and you're trying to marry them manually, and there might be some guesswork there. With the 3D data, it automates that and provides a lot more confidence. On the fly, as we're gathering data, we can also have variable inspection density. So you can, again, we're kind of comparing to the baseline of a UT grid where you're getting really a pretty coarse coverage of a pipe, but you're getting complete coverage, maybe on a 1-inch or 2-inch grid. But on the fly at inspection time, if there's an area that you want to study in more detail, you can get denser information there, closer to like what you would get out of a fully automated UT system. And lastly, the last thing I'm going to demonstrate is some cloud-based tools for really managing all of that inspection data. If you have a system that allows you to collect 100 times more data, it's really important that it's not 100 times more difficult to manage that data, right? Otherwise, people rightfully so are just going to go right back to taking a probe in their hand and walking out to the field with a notepad, because that's going to be the easier thing to do. So what we provide are tools that actually make managing this data even easier as it was before, again, to really remove that friction and make sure that you can actually get the most out of that data. So with that, I am going to shift over to starting some of the demos. Again, so I'm going to start off with an external flaw detector where I'm going to scan a weld and move to some corrosion mapping. And then we'll spend some time demonstrating the integrated solution for corrosion mapping, and then finish up with a demonstration of kind of the web interface for viewing scans and data management. While I'm getting that set up, anybody who wants to ask any questions can fire away. Willig will be curating them and handing them off to whoever here is best to answer them. So thanks, I'll be back in just a couple minutes.
Thanks, Dave. We have one question about pricing and availability and kind of what that all includes. I have Bob Rada and Gary Kroner here with me, so I'm going to pass those questions off to them. So Bob or Gary, whichever one of you guys wants to take that.
Sure thing. So this is Bob. Thanks, Willig. And by the way, just to be clear, the questions that you have, you can enter into the chat box, which you'll see on your GoToWebinar control. So if you just type a question in there, it'll go over to Willig and the moderator, and he will divvy it up as it makes sense. So as far as pricing and availability goes, the base system, sort of the base package encoder arm that outputs data to other flaw detectors, that is just about ready to go. So we're looking at a Q4 release for that system. Now Q4 is a couple of weeks away. Like I said, it's just about ready to go. And pricing is to be determined. Our expectation is that base package encoder arm will be in the ballpark of around $15,000. For the ARM plus the integrated UT thickness package, that is also expected to be ready in Q4, but we have a little bit more software work to do on that one. And really, we want to get some additional feedback from the field for the UT thickness package. And again, pricing is to be determined on that, but we'll call it ballpark 30,000 US for that integrated system. Back to you, Willig.
Thanks, Bob. We also have a question about probe compatibility. So like what kind of probes we can use and interface with. So if there's any examples for that, Bob, I guess you'd also be a good answer for that.
Yeah, I could jump in there, and Dave can jump in as well if he'd like. Yep. It's designed to be compatible with any system that accepts encoder inputs. And so we are doing an integration with OmniScan, with the ZTech Topaz. We're trying to be probe agnostic as best as possible. So it's kind of a general answer, but there's a couple of examples of flaw detectors that we're currently working with. If anybody has a flaw detector that you want to integrate with, or a system that you want to integrate with, then we would like to know. So you can reach out to us via our website or send us an email at info@hebirobotics.com. And Dave, do you want to add anything to that sort of generic answer?
No, I mean, that's really good. I think the important things to underscore is especially if you're using an external flaw detector, the compatibility is almost purely mechanical. So for instance, the phased array probe I'm going to demonstrate here today, we didn't even have the probe a week ago. And in the space of 1 week, we were able to basically 3D print a holder for it and essentially tell the software how it's configured at the end of the arm. So, and this goes beyond UT, right? So systems that do pulse eddy current or EMAT or eddy current or MFL, really, if it's a sensor that can be mounted and is small enough to be handled by hand, and if you have a system that takes encoder inputs, odds are an integration can be made fairly quickly. And as a company, one of the things that HEBI specializes in is custom integration for systems in general. So we have the ability to put engineering resources in-house on either mechanical or electrical integrations.
Great. We also got a question come in. What is the weight of the system? So Dave, if you want to talk about that.
That is a good question. The arm itself weighs about 7 pounds. Most of that weight is actually in the base. What we have right now, actually, now that I'm set up, I should be able to start sharing my screen. So give me just a second, and that should give you somewhat of a feel for the size. So my setup should have changed a little bit. So there's a couple different things that you'll see here. What I've got is the map system set up here. Like I said, it weighs about 7 pounds. It depends on how many knuckles you have put together. This system here is what we call a 9 degree of freedom system. So there's 9 joints. There's 1 at the base, and then there's 4 knuckles, and each knuckle has 2 joints or 2 degrees of freedom. At the end, I'm starting off here with a phased array probe, and we've 3D printed a holder that basically holds it relative to the end and guides you in moving perpendicular to the probe for doing the inspection. And the base here, you can see, has these kind of flexible ball and socket mounts and magnetic clamps. That's kind of our first stab at a general purpose mounting mechanism. The whole system is waterproof as it dunks into the tank here. But really the important thing to demonstrate about the system is basically the base just has to be fixed to something. So I'm clamping it here to the pipe for convenience, but really you can clamp it to anything nearby, whether it's a support or if you need to take these off and use ratchet straps to mount it to something, you can do that. So like I said, the system is, we're focusing on keeping the system as lightweight as possible and as small as possible. and with the idea that in a lot of cases, people might be doing these inspections by rope access. So being able to have it be put in a backpack, carryable by a single person is important. So now that I've got the system fixed down, you can see I've got the probe here. This is actually the probe element, and you can see I've got an Omni scan off to the side here. I've got a second view where you can see the Omni scan that I'm going to use for integration. So once you have a map system set up, the first thing I'm going to demonstrate is weld inspection. So we have down in the corner here is the app that we launch. There's a fun little splash screen. And then as long as we're on, there's a box off behind the camera. It's about the size of a shoebox that has a Wi-Fi network that the iPad connects to wirelessly. So you'll see there's a wire connected to the iPad for the demo here, but that's really just so that you guys can see the screen live. The entire interface is wireless so that the operator can move around. So you'll see some options along the top of the screen in terms of different flaw detectors we can integrate with. We've got kind of a generic quadrature encoder output, but we're looking to work with OEMs to make integrations as seamless as possible. But right now we're going to select that. There's different configurations of the arm that you see here. I have the one that has 9 joints, 9 degrees of freedom. And in this case, this phased array probe that I've got here is something we don't necessarily have in our library yet. So we have the ability to customize basically where the probe is relative to the end of the arm, which is the last piece of information we need in order to kind of know where it is in space. So we designed this mount so we know that it's 100 millimeters down in Z, 64 millimeters over in Y. We'll set that configuration and we will continue. So we've got a couple different types of surfaces we can create. I'll get the pipe elbow at the end. What I'm going to start off with is a weld. And so what I'm going to do is add waypoints to demonstrate the weld. I don't actually have a complex weld around a nozzle. So what I'm going to do is make a fake weld out of blue tape. And I'll start back here. And I'll just kind of curve it over. So if this were like the nozzle on a vessel or maybe part of a saddle on a T, anything like that, as long as you can put a chain of points along it, you can train that into a surface that then the Omni scan or whatever flaw detector you have will understand. So what I'm going to do is basically move along the surface here, and I'm going to touch the iPad and add a waypoint. And I'll move a little bit along the weld, add a waypoint. And so if the curves are relatively gentle, you can space these points out pretty far. If they get tighter together, like at a corner, as long as you put points kind of on either side of a corner, you'll get that sharp corner in your registration. So once we've added our 5 points along here, you can see that we've added them in the interface. I'll click validate, and what that does is it shows the points, gives me a rough view of what that weld looked like, kind of starting and moving around in that curve. So then I'll create the surface map, which is that smooth version of it. And the lines actually show you kind of the direction the probe is pointing. That shows you how it's going to unwrap that surface as a flat map that we're going to send to the flaw detector, the Omni scan. Okay. And now in the case of an external flaw detector, what we have is some things that we need to set basically on the screen there. So you'll see it says X extent is 659 millimeters. So what I have to do on the Omni scan area, scan end, Is the OmniScan screen updating for you guys? Can you guys?
Yeah, I don't think so.
I think it's running really behind. Let me try to fix that real quick.
While you're doing that, we had a question come in. What is the max temperature of the component we can inspect?
The max temperature of maps is in ambient. It's around 50 degrees C. Now that's if you do nothing to keep it cold. So one of the reasons we made the map system waterproof was so that you could actively cool it with water. That's really also going to depend on where you mount the system. So in short, I think the main temperature limitation is going to basically be the probe for whatever you use to inspect the surface. So if you have a high temperature probe, up to, we're hoping to be able to get up to things that are about 350 degrees Fahrenheit. So if you could do things to block heat from radiation, mount the system where the base is further away from the hot thing you're inspecting, and the whole thing's waterproof so you can spray it down with water. We think we should be able to inspect assets that are that temperature, but that's something we're working toward this year. The short answer is we have not tested it beyond ambient yet, but we've engineered everything in place to allow it to run at higher temperatures. So that should show. It's a little bit delayed, but now you can see what's going on the OmniScan. So back to here, I need to enter, let's say 659. So that's essentially the length of the weld, that unwrapped length of the weld. And I've got that entered in. And so now I'm going to get ready to start here. And I'll turn on my bubbler. Start spraying some water. Okay. And then the first thing I do is I start my OmniScan, and then I'll move the probe into place, and I'll start the probe. So as I move it down across the weld, you can see kind of my progress on the iPad app, where I'm seeing that move along kind of the middle of that stretched out surface that I trained. And let me give it a little bit more water for a little bit more air. And then maybe more intuitively, you can see that 3D view. Unfortunately, it's showing on the inside of that surface instead of the outside because I trained it going the wrong direction. But I can follow that along. And again, back on that 2D view, kind of shows me my progress. And I will freely admit to not being a UT level 1, 2, or 3 inspector. So I do not know if I've set up the phased array parameters right. But kind of the key thing is somebody who does know how to set those up could then go back and if you need to do multiple inspections, set them up again. But again, this is absolute, so I can do that section. And then if I need to pause, I can move the system around here, resume. Kind of move around like that. All right. So that's weld inspection. So again, the process is roughly the same on really any any flaw detector that does phased array and has at least one encoder input. And we can do straight welds as well if needed. So if there are any questions specific to that, I can address those, or I can move on to the next part, which is corrosion.
We had a couple questions, but you can start switching over to the next demo as I ask them, and we can either have you answer them or Bob or Gary. So the first one is, what does the red dot mean on the screen, which is actually pertaining to this demo?
No, that's a good question. So you'll see this in both modes. Let me turn this around if I get the probe. In this case, when the software knows how far away the probe is from the surface. So if I know, again, this kind of goes to this goes to OEM integrations, where if we move far enough away, that's a tunable threshold, right? So that distance threshold. If I move further away, that knows that you're not on the surface. So you could pause scanning automatically, throw an alarm, various other things based on that. And I could tune that to be, extremely tight right here and have it trigger almost immediately, or I can make it, much looser. Maybe if I was doing something that had a much wider kind of range, like pulse steady current, something like that. So that's what the red indication is either I'm not normal to the surface or I'm not close to the surface.
Great. Another question we had is, does it only work with water couplant?
No, we use water couplet for convenience, but again, the system really is probe agnostic. So if you have a probe that needs to be coupled with oil or something that maybe like for high temperature, right? As long as you can mechanically mount the probe, we can work with whatever couplant, whether it's applied manually. If you need us to work with some sort of solution, help dispense that, we can work on that too. So again, this isn't just water coupled, and it's not even just UT. Everything I'm demonstrating here is UT because that's a common technique. But at its core, what MAPS is it's really just measuring the position of any probe, as long as you can do the integration from there.
Great. And as you're finishing up, switching over demos, to add on to the max temperature question, there was also a question about adding a temperature sensor to the probe holder, which I can actually answer. The great thing about this kind of technology is that it's reconfigurable and it's custom, especially with the probe holders. So we can always customize and add things like temperature sensors to that kind of technology. And Dave, if you want to add anything to that.
I'll add that the knuckles themselves already have temperature sensors in them. So we're not sensing the surface temperature necessarily, but you do have temperatures from the knuckles themselves. So you have a really good understanding of kind of the ambient temperature throughout the arm. But yes, like we can very quickly add in other sensors of various forms. Under the hood, this is basically built with the same technology as the platform that we use for research. So it's just standard Ethernet up and down the arm. So there's a lot of flexibility in us being able to add and customize things quickly.
You got time for one more? Or are you almost there?
Oh yeah, fire away. Actually,
this is probably a good question for Bob or Gary, actually. So we'll let you focus on switching over the demo. Do you guys provide any training or support for these systems?
Yeah, this is Bob. And yeah, so we are bringing this to market in all likelihood via OEM relationships. So in that case, our plan is to make sure the OEMs are well equipped with the know-how to get their customers up and running. But we also plan to sell direct, especially in the case of the fully integrated UT system. So we are the plan there is to sort of train the trainer. So especially at the outset of a relationship, we'd be on site to make sure that the team that's using the system knows how to get it going. Again, sort of teach them to fish, train the trainer so that they can be self-sufficient moving forward. But customer service and ease of use is incredibly important to us. We know that we need to work really hard to ensure that the system is rugged in the field and is easy to use out of the box, and make sure that the end users have all the tools and the knowledge at their disposal to make it go. So sort of a multi-layered approach to training and support.
Okay. So now I've got the corrosion probe back. This is a Euro style dual element contact probe. In this case, I've got a holder built into it that spring loads the probe against the surface, has some magnets to help clamp, and has, again, a water bubbler. But again, to that previous question, we could work with gel couplet or anything else. I need to load the setup that I have for corrosion mapping.
So while you're doing that, we did have a question come in about adapting the system to use multiple element transducers. So would this be a perfect example of that?
Yes, so this is a dual element transducer. What I was doing before was phased array. Again, my understanding is that there's ways of splitting out that phased array to multiple transducers. In short, if you can mount it and the flaw detector can handle it, we can handle that. What I'm going to show in the integrated solution later on, what we're providing is going to be single channel, could be dual element, like pitch catch probes. But again, if the flaw detector supports it, yeah, we can work with you to mount them whatever way makes sense for that. So I'm going to complete the scan. And what I'm going to do is go back to the beginning here. You'll see that the inspection that I just did is getting uploaded. I'll talk about that later. I'm going to go to contact probe because I've changed the probe setup. Set the configuration. I'm still going to use the external flaw detector that you see up top. In this case, I'm now going to set up a two-dimensional surface. And I'm going to start the probe over here. And I will add points just like I did before. But now I'm going to do them in kind of a two-dimensional grid over the outside, the extra dose of the pipe elbow here. I'll do a 3x3 grid. Just like before, there's a step where I'll validate. Now I see the points roughly connected with that surface. Then I can see that 3D map. I can see how that map unwraps into a 2D surface. And if I'm happy with that, I can continue. So again, I come back to that same screen. So now there's two sets of things I need to put into the flaw detector. So I'll go to scan. Got my area set up. So I need to do 219 millimeters in X. X is my scan direction. I need to do 283 in Y, my index. I'll make sure my encoders are set right. 20 steps per millimeter. Basically, the system we have simulates a wheel encoder that you could send to these systems. The key thing is you just want to make sure the number that we have here that you see in the iPad interface, in the inspector interface, matches the number that you set on the scanner here. And again, that's something that's configurable. It's a little bit different on every flaw detector, but the base feature is there. So we'll get ready to start, just like we did before. We start the OmniScan, and then we start here. Whoop. Resume, and I'll set the grids to match because the OmniScan set to roughly a 10mm grid. And what you'll see, I don't actually have the right connector for the OmniScan to take in the probe information. But you can see that what I'm building on the iPad, which is showing coverage, is being mirrored on the OmniScan. So if I had the right connector, I would be building up a corrosion map just like I would if I had an automated UT system moving back and forth. So for instance, I would set that, if I was doing a UT grid type inspection, I would set that to be something like a 25mm grid or a 50mm grid, and then move through those cells. So there's not as much to demonstrate there because I don't actually have the right hookup to the OmniScan, but what I'm going to do is now switch over with this same surface. I'm now back at this first screen. I'm going to go to the integrated application. I don't have to change anything else. I'll set that configuration, continue. I still have the surface trained from what I had before. So I'll go through that validation procedure again. I'll create that map. I'll continue. And now what you'll see is I've got basically everything needed to do the UT thickness in the app. Inside the box that I'm connected to is a pulsar board. That's what these cables are now going to. And as soon as I start up my bubbler, you can see the A scan down below. And as soon as I unpause, I can start moving over the surface and building up thickness as I go. So this is doing a 10mm grid, so a little bit tighter than a 1/2 inch. And our approach to data in this mode is a little bit different from what traditional flaw detectors do, where the data is always associated with the grid, and only one grid cell can ever have a thickness value associated with it. What we're doing is we're essentially measuring all the data online, and we're still displaying a number, a single number to the operator, but it is either the average, or the median value, or the max value, or the min value that you saw within that cell. So for this patch here, this might be something that somebody might normally lay out with grid points. So instead of actually physically putting that grid on the pipe, we essentially have a virtual grid here. You can't see it yet necessarily in the white space, but that's something we can add. And you can very quickly essentially move the probe, cover that in. And if there were, for instance, a support that you couldn't get to, say like in that area there, and I was working around a support, you would explicitly see that, right? So rather than having to hand annotate things that you couldn't get to, it's clear right there in the map itself. And then the next thing I want to demonstrate with this is basically the ability to do variable density on that data. So I'm running on a 10mm grid here. If I wanted to say, look at that low spot in the bottom left corner there, I can increase that density down to 2mm, and I can go do that in more detail. Now, whereas if I wanted to do this on another flaw detector, I would have to essentially throw out what I was doing before, or do a separate inspection and align them later, and now I have to keep track of 2 or 3 or 4 or 5 different different reports for the same object. Whereas in this, it's still the same scan. You know, it's still exactly the same setup, and you can just gather more data in that one area on the fly. So this is getting you density of like something like closer to what you would get if you had an automated inspection system. You might be gathering data every 50 thousandths of an inch or every 1 millimeter, and you can get down to that. So the arm has a accuracy of about plus or minus a centimeter, has a resolution that is less than 0.1 millimeters, so a couple thousandths of an inch. It's just that on a practical standpoint, from a human standpoint, it's a little bit tough to do over a wide area, and we will be moving toward more automated solutions for that in the future. But no matter how tight I go in there, I can zoom back out. Oops, that's 1 millimeter. I can zoom back out, and that previous data is all there. But if I want to, again, go back in 2 millimeter, that's there. And again, I'm viewing it in the 2D mode to be able to really zoom around, but this is often a more intuitive way to view the data as well. So there's the probe position in 3D. There's where you are on the surface. And if I wanted to look at that defect, that indication in detail, I can zoom in like that.
And Dave, if I can just butt in real quick,
yeah.
Even though you are sharing the OmniScan right now, that's actually not any part of this current setup. So I just want to make that note.
I'm going to close the OmniScan view now. That's correct. I should have closed that down. So now everything I'm doing from here forward is just the iPad. So you'll see the iPad view on the left, and you'll see the webcam view on the right. Yeah, thanks for prompting that. The last thing to show on the iPad side is, again, I'll go to continue. We also have the ability to, instead of just doing a general surface, we can kind of shortcut that process if we have knowledge of the geometry. So in the case of starting with pipe elbows, where we could add T's, reducers, any sort of standardized geometry, you can choose the pipe size because that's a standardized size. You can choose parameters, whether it's a short or long elbow. And now if I give it only 2 points on the start and end of the extradose, and if I give it 2 points on the intradose, the inside, now I get a similar registration screen where it's basically locking those points to the known geometry of an 8-inch pipe. And if I unwrap that 2D view, you'll see you kind of have this, I guess, sort of wrestler belt sort of shape that unwraps for that. And I'll get the same thing that I had before. And I can do, for instance, 25 millimeter 1-inch grid. And once I get the bubbler going again, I can do the same thing as before. Now, whether or not I'm inspecting the whole surface, I still have that registered to a known geometry. So even if you're only inspecting the patch, one part of an elbow, there's still advantages to registering it with this sort of geometry because it winds up being very consistent to what you may have done before with maps. It is something where it is going to be consistent with whatever inspections you were doing before. For instance, if you were doing a UT grid and it started, at the top of the extradose, using this sort of registration, it gives you kind of a better known kind of reference point for how you're going to incorporate, this newer data into what you did before. So again, for example, this is essentially the equivalent of a 1-inch UT grid, and I've been inspecting for just a couple minutes, and I've essentially, already done the extra dose. And if for whatever reason I needed to move around and do the intradose, I can bring this around and provide inspections on that side as well. And again, we've got the A scan that you see below. What I'm inspecting with right now is essentially an automated auto correlation method. So it's basically a parameter-free, reliable detection of thickness as long as you have multiple echoes. But we have support for standard and echo to echo settings as well. So you can inspect this just like you would with standard UT with a handheld system. And what I'm going to show next is basically the tools we have for managing this data and reporting. And you'll see that part of what we include in that is the raw A scans. All of those raw A scans are also being captured in addition to just having the map that you're seeing here. So again, this is an integrated solution where specifically for corrosion mapping, we think this really kind of jump starts traditional UT thickness. There's a lot of cases where people, I think, may be going to phased array now, going to a more expensive system requiring more highly trained operators, just so that they can get full coverage. What we're hoping to be able to do is help them get full coverage, help them get data like what they're currently doing with UT Grid, but getting it faster, getting it more reliably, and more intuitively with a more kind of widely available set of operators, people that are trained at maybe just UT level 1. All right, so this would be another good point for questions while I get the web demo set up.
Yeah, we had one question. You showed the different scaling options for the scanning, but in terms of accuracy and repeatability of the ARM system itself, can you speak to that?
Yeah. So right now, the map system that I demonstrated here is about plus or minus 1 centimeter. So if you were to anchor, put the arm down in a place, where you are to maybe within about a 1-inch patch around that location. The accuracy does depend a little bit on the configuration. So it's a reconfigurable system. If you use fewer joints and shorter links, your accuracy and repeatability will be much better. If you make the links much longer and you add more joints, your accuracy will kind of grow. That uncertainty will grow roughly proportionally. So roughly a centimeter, but it does depend on the configuration.
Great, thanks, Dave. And I just want to remind everyone, since we did just pass the 1 hour mark, if anybody has to go, has a meeting or anything else they have to attend, we are recording this, so we can send out the recording after the fact. So thanks again for joining, but we do have one more demo left that Dave is going to do right now.
Yep. So if you go to this is kind of the prototype of the website we have set up for showing reports afterwards. Basically everything that you see that got uploaded in, let's see if that reloads. Everything that I've been doing for this whole demo has been getting uploaded to basically a cloud service where we have all of the scans, the information, things where you, for instance, where you see false here. This is all just kind of a prototype of the kind of core functionality. But these are scans that went to the OmniScan, so I have just the motion of the arm, but I don't have the thickness data. This is one that I prepared this morning. Oops, that's not the one that I prepared this morning. This is the one I prepared this morning, where I registered the elbow, I inspected it. You see basically the same thing that I did in the iPad app with that grid. Here you can actually see the gray lines of the grid that's yet to be completed, kind of analogous to a UT grid scan. If I mouse over the areas, you'll see the thickness changes. So this is actually a small part that I dremeled down into the pipe by hand to give a thin spot. The thicker parts of the elbow are closer to 9 millimeters, 8.66 millimeters. And again, I have kind of that variable density there. So if I change the grid size down to 2, you can see a pat 2 millimeters. You see the grid got much denser. But this is an area that I filled in with more detail, so I could move in there. And again, I also have that intuitive 3D view available as well. And although I didn't fill it in for this particular scan, we have the ability to tag all the inspection data along with it as well. The inspector, any sort of information about the asset, it's kind of everything that you would normally have in an inspection data management system. And lastly, if you click on any one of these points, what you'll bring up is the representative A scan that's being used for that thickness. So if for whatever reason you need to verify that data after the fact, again, you get everything so that the operator in the field has a lot of confidence in what they're presenting, but there's full traceability back all the way to the A scans so that you can verify, okay, what is the signal that's giving this number, and making sure that I can trust that. And again, this coverage here, including that patch there, was covered in about 7.5 minutes. So really the name of the game in leading into all of this is really speeding things up, saving time, in addition to getting better, more verifiable data.
So we had a question come in about that demo, Dave. Can you reverse the color palette?
Reverse the color palette? Not yet, I don't think. That is something we could do pretty easily. Let's see, if I drag this and it goes negative, it floors on that color palette. I can adjust the color palette, right, on the fly. I cannot reverse it, but that would be the sort of feature that we could add fairly quickly. All right. So thank you, everybody. Apologize for going a little long, but just to wrap everything up, what we demonstrated today was MAPS, Universal Absolute Encoding System. We did showed two versions, two applications of it. One is where it's used as a virtual absolute encoder, where it can inspect any generic surface with the advantages of not having wheel slip, but really just plugging into any existing system you have right now that talks to a wheeled scanner. We also demonstrated techniques for next generation UT thickness that inspects significantly faster than what you get with moving with UT grid and manually painting grid lines by hand and managing that data, and showed kind of an intuitive system for the operator, and demonstrated the tools we have that we're putting in place to make that data more easily manageable. Really the last thing I want to conclude on is, I showed where HEBI came from. I showed where we are now. We're still running very fast. And so in the world of NDT, we really think this is just the beginning. To date, we have really thrived by getting really great feedback and having great interactions with our customers. And that's helped us move them forward, and they've really helped us move forward. And we think this field's exactly the same. So if you have applications, questions, ideas for maps, or really any other inspection needs, especially if it involves access to confined spaces or things that involve challenging manipulation, control, access, please let us know, because that's really what our team here excels about. So with that, thank you for your time. And if you have any more questions, contact us from email or visit hebi-ndt.com. Thanks.